Okay, let's continue. And now we are going down to the bottom layer, which is physical design. Well, when we talk about physical design, we are talking about what is the real layout eventually. You need to have some kind of floor plan. How do you put the major module in which position? Okay, in the plan, and then the standard cell, where the cells and how they are connected by using present rod. Present rod meaning how you connect the wire between cells in the layout. And then they are paired, such a slide, this slide, and we are going to show that in a minute. And then you might want to estimate the chip area. Okay. So this is the main floor plan. Here is their path, the control. Based on the MIP CPU, we are trying to design. And then the final layout for the chip. Well, actually you cannot understand anything, but typically, if you look at the layout and the circuit looks regular, things like this, look very regular, it means that you replicate many copies for the same circuit. Sometimes it's like memory or register. And we notice that on the boundary, there are many circuits here. Each one is one. Each one means one pin. That's a pin connected to the outside. And each square here is the I/O pad. I/O pad is a circuit rod that could drive the wire to the outside. Because inside the chip, the wire is very narrow, very thin. But in the outside, on the circuit board, the wire is very big, large, and long distance, right? You need to have very strong driving capability to drive the signal. So before you drive the signal, either 0 or 1, you need to go through the analog circuit that can provide very large driving capability to drive the signal onto the circuit on the board. And likewise, when you receive the signal from the outside, it could be outward, could be input, could be bidirectional. And each one needs an I/O pad circuit that can provide the required signal strength to going out or getting in. So you can view that it's some kind of interface circuit. And actually, in industry, you need to have at least VDD and ground, right? VDD and ground is the power wave that provides you the power supply. And if you look at some chip, it might have more than one VDD and more than one ground. Sometimes even for like 1/3 or 1/4 are the power wave VDD and ground. So many VDD pins and many ground pins. Why is that? Because we want to provide the VDD and ground a very, because the current from the outside should be large enough such that the circuit operation should be heavy, will be stable. If there's only one VDD and one ground pin, then the wire is probably not wide enough. And when a large current goes through another wire, that's going to to have a large voltage drop. The wider, the more stable for the signal, going up or going down. So that's why it could be many pins for VDD and ground. This is the layout for the standard cell. We call that one row and one row. Okay? For each row, there's a typical layout for cell-based design or standard cell design. Either one is fine. The VDD rail here, one rail here, VDD rail and one rail. Provide the power supply for each cell. This cell is inverter. Can you see that? Input A, output Y. The PMOS transistor, NMOS transistor. You can see that this cell is very wide diffusion. And the name two input NAND gate. The two NMOS transistor in serial, two PMOS transistor in parallel. The NOR gate, two NMOS transistor in parallel, two PMOS transistor in series. The three input NAND gate is N or invert. Okay? Two input AND gate, two input OR gate, and one inverter. The flip-flop, okay? The flip-flop, the layout. And the multiplexer, two input multiplexer, so on and so forth. There are many small standard gate layout for in the library. You can simply, just like you build a house. Here's a brick, here's a mosaic, anything. Many components, and you can try to build a house using that component. So it's just like that, doing the standard cell design. Uniform wear height. You can see that the height is the same, no matter for simple circuit or complex circuit. Their height should be the same, such that you can simply connect, right? Simply above. 就并在一起，接在一起，立刻就用 power rail can go through straight line. Okay, and also the output can connect the input, something like that. So easier for you layout if they are the same height. 通常是高度一样的，这样比较好并接在一起。And without violating design rule. Here we have two levels for the metal. Metal 1 for VDD and ground. And that's in blue. Okay, blue is metal 1. Okay, for power. And metal 2, SN to IO. The A, Y, A, the input signal and output signal using the second layer for the metal. Because if they are using the same metal layer, it could be touched together. That's the wrong design. They just like the bottom layer in this direction, going horizontal, and on the top is another layer for metal going horizontal and vertical, just within the space. 就我们今天至少有2层 metal. You should have at least 2 levels of metal. Otherwise, it's very difficult for the layout. And many processes provide even 8 layers, 9 layers for the metal. Just like the highway network going through. So blue one is metal 1, purple one is metal 2. Blue metal 1, purple metal 2. That way they can cross each other without touching each other. And that also includes where the substrate tag, we mentioned that before. The black dot is the where substrate tag. It employ the gravity. Hopefully they can be duplicated many copies in the layout, so we don't have to design you don't have to spend too much time designing your own circuit. This is sensor controller, control unit. After the sensor, this is the layout. You can see that one wall. And many cells here, here. Each block is a cell. One wall. Cell, cell, cell. And sensor actually need to gain level name list. And based on this library, you have the layout like this. And press and one using standard cell library. So that's the output of the press and one step. Using standard library, you have the layout and press where and how do you work, how do you connect the input output pin. We can see that between these two different rows, there's a space here. Here. We call that channel. We call it channel. This is not the same channel in the transistor layout. Okay. This channel is for routing channel. So what do you see from here? For example, if this cell, just take an example, assume that this cell will connect to something like that, should connect to here, okay, like this. The output, one of the output of this cell will be connected to the input of this cell. Then it will utilize the channel here, this is the channel. One of the wire in the channel. Connect here, and that way you can connect the two cells. And maybe another one, like there's a cell here, is going to connect to here. Then you can use another chip. Something like that. Well, actually, this should be different color than individual. Okay, purple, and then horizontal is blue. Let me try to use another different color. Try to distinguish between the green. Okay, like that. Vertical, the purple color, horizontal line, green color, and this is contact. So these two wires do not touch each other, right? They just simply cross it. Okay. That's why you need at least two metal layers. Okay. And then you can imagine that it's important how you press the cell. In here, this is not a good design. A better one should be one. For example, if you interchange these two cells, then what? What do you get from the layout? If this cell is put here, this cell is put here, that should be different result. Which one is better? The new one is better. Why? Why? If you change these two cells, it's going to be a better layout. Why is that?
比较近。
If you change, then
是吗？比较近，比较快。
you need to change. And then What's the benefit by doing that? By doing that, this horizontal line could be the same line, the same thread. You don't need two different threads to connect these four cells. And then your channel, right channel, can be narrow, saving some chip area. Right? Let me repeat it. Before, this connect to this, this connect to this. And you need two different tracks in the right channel. Because otherwise they will going to be overlap, touch together. But if you exchange the position for these two cells, this connect to this one, this connect to this one, and they can share the same track. They only use one track instead of two. That saves some chip area, right? So likewise, if there's some other cell connection, maybe here we connect two cells like that. They also can connect using the same track. They can share the same track. You don't need too many tracks in the right channel, right? So plug and lock is important, especially for the chip area consumption. So one of the goals is to reduce the chip area for the routing. And another goal is hopefully the wire should not be too long. The longer the wire, there's going to be more delay for the signal propagation. So this is one of the CAD problem, computer aided design problem. They are involving many complex areas to solve the problem. There's one reduction area. And like I said, typically the cell should be about it together with the same height. Since I controller area is mostly wire, design is smaller in one store over cell. So many wire can on the top of the cell, just like the freeway or the highway can be in the sky. Okay, then you don't need to consume too much area, too much land。可见是可以立体的，公路在天空上跑，下面是房子，那这样可以省掉很多道路空间。Okay? It's smaller and faster. Okay, signal will not propagate too long distance. Low power consumption also. The shorter is better, the smaller is better. Design snap together, 连在一起 snap together, cell for their height and array like this. And plug wire into cell. Try to put wire on top of the cell without using the chip area around the circuit. Connect by abutment, just above. 就把并列在一起，就是重连接在一起的。A point, okay, we mentioned it before. In the structural design, we measure locality. Hopefully, when you generate some output, it can be consumed nearby. Okay? And if you generate some output result, it can be consumed as soon as possible. We call that locality. From temporal locality and spatial locality. 尽量在地化 local， 一旦讯号产生单，这个结果出现，尽量在附近邻居就把它用掉了。If you can consume the output locally, the circuit do not need to travel long distance to another corner on the chip, and that's going to be bad. Consume chip area, consume power, consume need more delay. And also, when you generate some output result, hopefully it can be used immediately. Then you don't have to store. You don't have to store the value. You don't have to have flip-flop or lag to store the value. And that's going to be a better circuit. Takes a lot of effort, okay, to come up with a design, a good design here. It is a mid pair path, 8-bit pair path built from 8-bit slices. The reality, you only design one slice, one bit slice, and then you replicate bit slice 0, 1, 2, 3, 4, 5, 6, 7, totally 8-bit. One bit slice is a 1-bit pair path, including flip-flop, including manipulator, including adder, so forth. All the circuit, but only 1 bit wide. You can replicate 8 copies. After that, there might be some actual circuit such that they can combine them together. We call that zipper circuit, to zip together all the bit slices. Zipper at top, drive control signal to their path.
功能听不懂。
So again, this side, the slice plan for this side. Each bar is a cell, and the wire on the top connecting. Here we have one channel, but if you have more metal layer, the wire can also on the top. So unless it violates the design rule, unless it touch the same layer, otherwise, not only the empty space, but also on the top, they can be utilized for the connection. So here you can see that the blue line are the wire connecting different cells in the same wall. Okay. This means that these pins are connected together here. Connected together. And cell ordering in dimension and wiring track are the issues you have to consider. Let's say, how do you order the cell? That affects your connection, right? Just like cell routing. How you order the cell sequence, that determines your channel, your routing, or wire connection. Okay. And we prefer the shorter the better. Okay. The fewer track, the better. We try to arrange the cell such that the wiring locality is good. And this example is instruction register here. Okay. This is for VLSI. This slide, VLSI. The source A, source B register, point counter, LU. So the whole row is their path. It's 1 bit their path. And then we replicate 8 copies. It becomes 8-bit their path. And then you can try to estimate the chip area, because that affects your layout, your floor plan. We need area estimate to make floor plan. Well, it's typically based on impurity. So for example, here it shows some number for different circuit style, circuit type. Random logic, given 2-level metal process, each transistor consumes 1,000 to 1,500 lambda squared. You might wonder how come it's so much for each transistor, but you have to know that the chip area not only for the circuit transistor, but also for the surrounding spacing for the wiring chip area consumption, you have to consider everything. So each transistor, you need so much chip area. Therefore, random logic, so it's much larger. But they are paired, a little bit more regular, so it's smaller. Each transistor 250 to 750. Okay. And for SRAM, each bit need 1,000 lambda square. But DRAM is smaller, 100. ROM also smaller, 100. So you can see that typically logic consumes larger chip area compared to memory cells. And then the design verification process. After you design is done, how do you know it's correct? How do you know there's no bug, there's no error in your design? How do you know that? You have to verify. It's just like after you write down your program, you should verify that there's no bug. You have to guarantee that it's bug free. But how do you do that? You have to do testing, right? Test the program. And for software program, the way you test the program is we try to provide some input data and try to run it and look at the output data, whether or not it's correct, right? And maybe one set of the data is not enough. You have to run different input data and look at the output. If something wrong, try to find out where is the bug, right, in your program. But how do you know which point, which statement is buggy? You might want to print out the variable during the running the program. Try to write down, try to print out the variable value and to look at, to check what step has problem. So that's the way to debug your program, try to trace the program. For hardware design, you also need design verification. It's very, very important. So nowadays, the verification group probably typically has more human power than the design group. For example, if there is a CPU group, the CPU group typically is design subgroup and verification subgroup. And verification subgroup has more people than design group subgroup. 验证，扩大验证里面的人，验证通常需要耗更多人力，比起设计团队。设计团队，你的 logic design 是circuit design, but verification you need to run many simulation. You want to go through many test input to make sure that it's correct. Verification is slow and expensive, so you want to make sure that the design is bug free. Otherwise, if it's wrong, you have to send the design to the fab again. It's very expensive. It takes a lot of time to go through the manufacturing process. This is long time ago for MOSFET process. 0.6 micron is very low level technology nowadays. $1,000, it takes 3 months. And for 65 nanometer, it's up to $3 million. It takes 1 month. And nowadays, 3 nanometer, 5 nanometer, 3 nanometer is going to be very expensive for the test run, for the manufacturing, the first chip. 所以今天晶片制造已经是非常昂贵的，尤其对高阶制程，或者是6纳米制程。它需要花300万美金，这也不便宜哦，300美金已经是多少？1亿台币了，已经是不便宜的东西。那更先进的制程，一个晶片要去刚设计好之后要送回去展，第一批是做测试用的，看它是不是可以 work。它有耗费金也是非常昂贵，很多小公司没有办法负担。万一要错了，要重来一遍，要花那么多钱，公司怎么就垮掉了？没有那么多钱。So debugging chip is very hard and very important. And what's the difference between hardware design and software design? from debugging point of view. What's the difference? And which one is harder? Can you try to imagine? My question is, when you design a software program and hardware chip, the debugging is similar. They are trying to verify that the design is correct. It's no bug. But is there any difference between software debugging and hardware debugging? Any difference? Which one could be harder or more difficult? Debugging chip may be even more harder. It's harder than debugging program because it's not easy to look at the inside signal. After you come up with the chip, okay, when you write variable code, fine, it's similar. You can simply print out the variable. But after the chip is manufactured, then the only thing you can look at, you can see, is the pin, the interface, the wire connected to the outside. You cannot look into the signal point inside the chip, right? For software program is a design product, it design result, it also manufacturing result. They understand? 对软体而言，尺码本身就是最终的产品，它没有什么具体的这个什么一点都没有，它尺码本身就是你设计出来的结果的最后的产品。那你可以在里面设很多 print 或 write 的 statement 去看每一个变数的这个变化，来找出哪个环节出了问题。For hardware design, writing variable code is similar to software design, but after the chip manufacture, you still need to test the chip is correct. That's very difficult because you cannot look at the value of the inside point. 当它晶片做出来之后，你是很难去验证晶片是正确的，因为你看到里面的讯号的值，里面有千百万个讯号点，而且那么小，你根本探针进不到里面去测每一个讯号的点的值是多少。So, limited visibility is a problem. And proving design is correct before building. Okay, 所以你一定要，因为你做完出之后的晶片要测试是很困难的，务必要在设计阶段就要验证它。You should try your best to verify that your design is correct before you send it to the foundry to manufacture the chip. Otherwise, you are going to have a lot of trouble eventually. So it goes through many verification steps, like logic simulation, circuit simulation, formal verification, layout versus schematic comparison, design and electrical rule check. On the right hand side is the design flow, 设计的流程. Let's look at design flow here. Start from specification, 就是设计规范. Spec, which is what this chip, what this system is going to do, what is the input, what is the output, how much the circuit speed is required, so on and so forth, and what the chip area limit. And the next step is going to be architecture design. Based on spec, you come up with architecture design. After you get the architecture design, you need to compare if they both meet with each other. 你要比较一下是不是吻合之前的设计的一个 spec. And then, based on architecture, you go down a level below, you do logic design. Okay. And then you have like adder, like flip-flop, register, so on and so forth. And again, try to compare if they are equal to each other. So find out if there is any difference between them. And after the logic design, go down to circuit design, transistor circuit, and then compare these two. And then go down to physical design, which is layout, and compare these two. And sometimes when you go down some level, and you find out that, well, it does not meet the requirement for the circuit speed too slow. Then you have to go back to actual design, to redesign your architecture. Hopefully, you can get faster circuit. Can go through many turns before it's finalized.
是那边是用中文的讲词吗？那个图可以用中文的讲词吗？那个图。
I'm sorry, let me try to repeat it in Mandarin. 这是一个设计流程，一个界面设计流程。一开始会给一个什么，就设计规范 spec。所以设计规范就是说，今天你要设计一个比如开车的这个地图导航，那它就会制定一个规范，说，我这个导航的系统需要有几个键、几个按钮，然后它能够显示地图，然后比如说0.几秒钟要更新一遍配合它汽车移动的位置改变的，要更新画面，这个所谓的 spec 的规格书，是你要全力以赴达成这个目标的一个要求，这叫 spec。那 based on the spec， 根据这个 spec， 我就开始去设计我的 architecture 的架构，能够应该是可以符合或者是实现它的 spec 的一个这样架构。你要确认一下这两者是不是真的可以互相是相等的。那给 architecture 之后，再下一个就是逻辑设计，根据不同的模组，我去设计里面的电路，里面很多是 sequential circuit、commercial circuit。那也是一样，你要验证它是否的确是相等的，是没有差错的。再下一步就是circuit design、transition 那个 level， 也是要验证。再下去是最后 layout 这个 design， 这样验证等等，这是整个流程。如果今天中间出的环节出错，比如说最后发现界面太大了，对我们刚出的要求是不稳的，或者说电路太慢了，不够快，它没办法符合要求，你就必须 go back， 从最前面呢，在某个点再重新设计，来修正它的设计，最后很可能要跑好几圈才会达到最后的产品的目标。有没有问题？ So you have to do many simulation, logic simulation, okay? Circuit simulation, logic simulation for functionality, the value of the 1 or 0, the value is correct. Circuit simulation, probably of the circuit speed, how fast the circuit is, okay? Whether or not you meet the requirement. The layout is schematic comparison to make sure that the design variable, the design rule, and finally, design electrical rule check. Sometimes even though the circuit is correct from the simulation, it doesn't guarantee that there's no problem. Because, for example, if some or two wires, these are totally correct, spacing is also fine. But sometimes, although they are correct circuit, but they are too close to each other, they still meet the design rule. But because of noise from the crosstalk, we call that crosstalk. Crosstalk means that signal traveling on different wires nearby, and they interfere with each other. From very point of view, 0 or 1, they are totally correct. But sometimes they could be interfere with each other when the signal transition. And that kind of design is not incorrect, no. It's simply that the electrical property has some problem. And you want to try to correct that kind of problem before you do the volume production. 所以今天有可能有设计都对，但是呢，因为讯号太接近，它会有一些干扰，或者说呢，有一些叫channel sharing. We might want to mention that afterwards, but it means that the capacitor has charge， 它们有电荷，那这个电荷呢，它的这个讯号有可能是，比如说电荷不够。不能分散开来，造成讯号的出错，类似这样子。Likewise, even though the logic value is correct, sometimes the electrical property is not good enough or is simply wrong. In that case, try to find out the problem. But anyway, verification is more than one half of effort on most chip. That's why we need more people, more verification people than the design people. Okay? Take a lot of time. And when we talk about verification, it simply means that the design verification, not the testing of the chip after you manufacture in volume. 我们指的是设计的一个验证 ，just like the program verification. But after you verify it's correct and you send it to the fab to manufacture in volume, you still need to check, you need to test each chip, whether or not each chip is correct manufactured. Right? 即便你设计对，不代表制造是对的，它可能中间有一些制造过程的误差，一部分是错掉的。你扣它EOL means that given 100 chip manufactured, how much the percentage is correctly manufactured? Maybe 90%. It means that 10 chips from 100 chips has defect. They cannot be used. You have to filter them out. You have to throw them into the garbage can. Only 90 chips can be shipped to the customer, can be going to the market. So after you finish your design, also through the verification step, there's a tape out final layout to the fab, to the verification. The 6-inch, 8-inch, 12-inch wafer, meaning the diameter of the wafer. Optimized for throughput, not latency. In the foundry, they concern about throughput, but not latency. It means that each month, how many chips you manufacture. Latency means that you start to manufacture the chip, and how much time does it take? That's for latency. Here we say that 10 weeks in the Moses process. For foundry, throughput is going to determine your performance. Throughput is going to determine your cost. 对晶圆厂来讲，他们在乎的是产量 ，because the equipment very expensive. They have to try to maximize the throughput. Maybe the latency is going to be somehow sacrificed. It takes longer. You try to schedule your manufacturing job such that it can try to maximize the utilization of the equipment because the equipment is very expensive. Even if it might take a little bit longer for each product. Okay? 即便它可能会对各产品会花比较久的时间，它尽量让晶圆厂能够越满越好，使用率越高越好，因为它要因为太昂贵了，所以throughput产量是它最在乎的东西。After you manufacture the wafer, then you try to cut into individual dies. Okay? We mentioned this before. The wafer, and then we try to cut it into chip. Okay? Each square, each rectangle is a chip. And after that, you get the manufactured chip. You try to package it in the chip here. And use the package and also bond gold wire from the die IO pad. We mentioned it before, right? IO pad. IO pad is this. IO pad. The wire on the outside. And inside is also wire. Okay? Connect to the circuit. And this wire, there are many wires here. and the material is gold. Okay, very expensive gold, but it's very thin, so should be okay. Should be okay for the cost. One gold wire from diode here to packaging the pin. But why do we need that? Why do we need to package the chip? 为什么需要封装 for that packaging? 产业封装。为什么需要封装 ？Well, the signal, the pin, the wire is very small, but you need to connect to the other chip on the circuit board. The circuit board is very large, the wire is very large and long. You simply cannot connect directly. You have to from small to large. Okay. Besides that, heating is a problem. If there's no such material in the large chip, it's not going to be easy to dissipate the heat on the circuit. Right? For example, for a CPU chip, it might be something like 60 volt. Just like a light bulb. 它一个很典型的 CPU 晶片就是60瓦 ，just like 电灯泡 light bulb. It's very hot. That's why we need to have packaging such that the material can try to dissipate the heat, 会让你的散热会容易一些。And even if we have this kind of packaging and it's not enough, maybe you can put a fan. 你可以加一个小风扇 to dissipate, okay, the fan beside the chip on the top of the chip. If that's not enough, still they can even have some kind of liquid flowing through the chip to carry out the heat for some special circuit, for some supercomputer. They can have liquid to flow through the chip to get away the heat. Okay, let's take a break.
No, 你先忙完。刚刚讲太快了，输出是什么？什么产量？等一下，我要重问。这不行，会不会这样刻？这是什么？
你说是它不是有
草图吗？
对啊，
哦，
是它的怎么讲？
草稿、草图、设计图。
对啊，是你记得那个处理器不是长，就是长这样吗？外面都是 I/O， 中间是一个处理器。
我只知道看到后面的实体之后，我才推回来才知道这是草图。然后这个呢？这是什么？这它有什么？有很多 VDD 跟光有什么东西？
哦，他说因为你的里面有很多东西要接到 VDD， 所以如果你就一个 VDD 的话，你的线不够宽的话，就是就压降会太大。如果线不够宽的话，不是会压降会更大。
就有点像延长线上面插很多东西的感觉。
对啊，所以就是要让它宽一点。所以它就要放多轨比较好。
压降会太高吗？如果只有一个 VDD 跟光，压降会太高，还是写说一个 well 一个 well 的负载会太大吗 ？VDD 的就是单个 VDD 跟 ground 的负载会太大，还是 well？
我不知道，我忘记他说。 忘记他说那个电压降太大怎么样？那它的目的是要让它的电路是稳定的。哦，还是说压降太大，所以那个电路就不稳定？啊，对，应该是这样。
这里是线路，所以是 VDD 跟 ground 不稳定，所以会造成。
没有你。
到底什么东西的压降会太大？
就是你的 VDD 不是要通过线接到你的。
对啊，所以是线上面的。
对，所以你这个线电阻太大的话，就是这边两边会差很多。
哦。哦。哦。
应该是这样。IC 设计的这个流程里面，唯一我觉得我能做的只有设计。
验证不行吗？验证也是写个 log。
验证很烦啊！我那个人工智慧资料处理我都不想处理。
那这边讲什么他这边是指说空间吗？这边我听得懂，就是等高。这个 well height 是什么？这个。这两个是指。
是这个 N2 的高度吗？一样高啊。
这个。
就是要分两种线。
两种金属。
两种金属。
我那时候没有听懂，他说两层平行，然后说一个垂直在干嘛？
什么哪里？
我不知道他下面在讲。
它的 metal 就是对啊。这样你就是。
那 vertical 是干嘛？
它可以接在一起啊，它可以。是你画了要的时候才可以，你就不用那个画翘过去。就是它的金属是分两层。
可是这边会要走一层。
就是你把它拿开之后，就是它不是要一层一层一层厚吗？
对啊。
对啊，它金属就要两层，至少要两层，要区分垂直跟水平的。就一个线是淡蓝色，一个线是深蓝色。区分的，这是要区分的。不然如果两个，不然你水平跟垂直在同一层，那你这样不就交叉在一起了？
对啊，是这边这个图表示出来。
应该是这样的，就是我觉得是这样的。
所以它这是两个。
所以它这个这个上面是 N1啊。它里面的是。
所以它只说直的这个是 M， 还是只说 Y 这个？好，我懂了。
我不知道是不是分水平跟垂直啊？它这里是。
我知道。他们说他们应该说 VDD 跟 GND 就是
另外一种。
A 跟 Y 不是 input 跟 output 吗？那它可能是在上面那一层，然后 VDD 在下面这一层，然后就是这样画下来是吗？
对啊，就是两个高度，两个 不同层的。
那这个regularity一般性。
就是他刚刚讲说要可以一直复制，
可以复制好几颗是吗？就是这个元件可以复制好几颗。
对啊，就是他们 regularity 嘛，就是长一样的，有规律。
好的，他讲太快了。哦，它这个的话是指说它的那个 tab， 就是上面算的那个 tab 就可以少一条，然后让这个之间变近，是这样子。
对啊。
这边就在讲这个。
所以后下面就跟你说要怎么做 cell ordering。
这边吗？
然后后面也会讲到。
还没讲。
就是有啊 ，database 不是有一个 database 吗？等我一下。这个。
对，我真的听不懂。
cell ordering。
这我听不懂。哦，这是指从上面看下来吗？
啊。
这是指从。
就是他刚刚不是说，就是可以调整让它的 track 数更少吗？
对啊，就是指这个图啊，这个图可以让它做更少。所以这个图是指说它从上方看，然后这样这个的话是从这个方向看过去，是这样子。就是
这也是上方啊。这只是它不是上面那个只是一个 cell 都画出来吗？它只是一个框框，下面写这个 cell 的名字。
我可以让老师在这边用中文讲，我听得懂这边。他说逻辑的这个。对啊，他说这个占的面积最大。
对，测试它的 area。
哦，我刚才想问一个老师问如果规格是跟它我们结构不符合的话，所以它如果最后达到的效能不是我们要的话，那所以是后面你要再回去两个测试吗？
就是你这两个做完之后，你要先测试是不是符合啊？那如果到这里。
的测试就是变成两个之间测试是吗？
就是你在做的时候，你在做，你要先定规格嘛。
对啊。
规格之后你要决定你的 architecture 要怎么做。然后这个决定好之后，你要先就是看有没有符合你要的规格。
对啊。
然后之后再往下，你要怎么实做这个结构嘛？
就是用什么单元？
逻辑的，对，就是什么 add 什么的那个，然后再看有没有符合你要做的那个结构，就两层做啊。
对啊，那如果到最后出问题的话，你怎么就是到底要怎么回去修改？
他就说到最后出问题就是重做啊。
他不是说这是可以回去找某一个吗？所以不可能。
他就是说从头做，所以就是改你的，比如说改你的结构，或是改什么逻辑之类的。就是要一直重做，就是。验证的无聊，我现在上厕所。